GenAI and MLOps Part 17. This episode has 8 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Scenario: hallucinated compliance answer. An LLM-powered support bot gave a customer incorrect regulatory advice that was later escalated. How would you investigate and prevent recurrence? Here's a strong way to approach it. Pull the exact prompt, retrieved context, and model version from request logs to see whether the failure was a retrieval gap, correct source existed but wasn't surfaced, a stale or incorrect source document, or the model contradicting correct retrieved context. Each has a different fix. Immediately add a disclaimer and human escalation path for regulatory or compliance adjacent topics if one didn't already exist. Then add that exact failure case to your evaluation regression suite so a prompt or model change can't silently reintroduce it. And consider a stricter policy, retrieval grounded only answers, or routing compliance topics to a human, for high-risk categories rather than trusting general-purpose generation. Nice. Let's continue. Question 2. Scenario: runaway agent loop. An autonomous agent got stuck in a tool calling loop overnight and ran up a large API bill. How would you detect this faster and add guardrails? Here's a strong way to approach it. Add hard limits first. A max iteration or tool call count per task, a per desk and per hour token or cost budget that kills the run when exceeded, and a timeout on the overall task, since none of these should have allowed an unattended loop to run all night. For detection, add real-time alerting on cost rate and call rate anomalies, not just a daily billing report, so a runaway loop pages someone within minutes. And add loop detection logic that flags when the agent repeats near-identical tool calls without new progress, so it fails fast and safe instead of retrying indefinitely. Great. Moving on. Question 3. Why is MLOps important in production ML systems? Here's a strong way to approach it. MLOps is important in production ML systems because building a model is only a small part of the overall life cycle. In real-world environments, models need to be deployed, scaled, monitored, retrained, and maintained continuously. MLOps helps automate and standardize this entire process, making ML systems more reliable, scalable, and reproducible. It improves collaboration between data science, DevOps, and engineering teams while reducing manual effort and deployment time. It also helps solve production challenges such as model versioning and reproducibility, automated CI or CD for ML pipelines, monitoring model performance and drift infrastructure scaling using Kubernetes or cloud platforms, faster and safer deployments, governance, security, and rollback management. Overall, MLOps ensures that ML models can operate efficiently and reliably in production environments at scale. Alright, next question. Question 4. Explain the ML life cycle. Here's a strong way to approach it. The machine learning life cycle is the end-to-end process of building, deploying, and maintaining machine learning models in production. It typically includes the following stages. 1. Data collection, gathering data from databases, APIs, logs, or other sources. 2. Data preparation and cleaning, removing inconsistencies, handling missing values, and transforming data into a usable format. 3. Feature engineering, creating meaningful input features that improve model performance. 4. Model training, training ML models using algorithms on prepared datasets. 5. Model evaluation, validating model accuracy and performance using metrics like accuracy, precision, recall, or RMSE. 6. Experiment tracking and versioning, tracking datasets, parameters, metrics, and model versions for reproducibility. 7. Model deployment, deploying the trained model to production using APIs, containers, or Kubernetes platforms. 8. Monitoring and logging, monitoring prediction accuracy, latency, drift, failures, and resource usage in production. 9. Model retraining, retraining models periodically when data changes or model performance degrades. 10. Continuous improvement, updating pipelines, features, and infrastructure for better scalability and reliability. In MLOps, the goal is to automate and standardize this life cycle using CI or CD pipelines, monitoring tools, and cloud-native infrastructure. Let's keep going. Question 5. What are the stages of an ML pipeline? Here's a strong way to approach it. An ML pipeline is a sequence of automated steps used to build, train, deploy, and maintain machine learning models efficiently. The common stages of an ML pipeline are: 1. Data ingestion, collecting data from sources like databases, APIs, logs, or cloud storage. 2. Data validation, checking data quality, schema consistency, missing values, and anomalies. 3. Data pre-processing, cleaning, transforming, normalizing, and preparing data for training. 4. Feature engineering, creating and selecting important features for better model performance. 5. Model training, training ML models using algorithms and training datasets. 6. Model evaluation, evaluating the model using performance metrics such as accuracy, precision, recall, F1 score, or RMSE. 7. Model validation, comparing the trained model against baseline or production models before approval. 8. Model packaging and registry, storing versioned models in a model registry for reproducibility and governance. 9. Model deployment, deploying models to production environments using APIs, containers, or Kubernetes. 10. Monitoring and logging, monitoring model performance, latency, prediction quality, and detecting model drift. 11. Retraining and continuous delivery, automatically retraining and redeploying models when performance degrades or new data becomes available. On to the next one. Question 6. Difference between DevOps and MLOps? Here's a strong way to approach it. DevOps focuses on automating and managing the software development life cycle, while MLOps extends DevOps practices to machine learning systems by managing both code and ML models along with data. In DevOps, the main focus is on application development and deployment, CI or CD automation, infrastructure management, monitoring and scaling applications. In MLOps, additional challenges are involved such as data versioning, model training and retraining, experiment tracking, model drift detection, feature engineering, ML pipeline orchestration. DevOps mainly handles deterministic software behavior, whereas MLOps deals with probabilistic models whose performance can change over time based on data. Another key difference is that in DevOps, code changes trigger deployments, but in MLOps, both code changes and data changes can trigger retraining and redeployment of models. In short, MLOps is an extension of DevOps specifically designed for managing the complete machine learning life cycle in production environments. Good. Here's another one. Question 7. What is model drift? Here's a strong way to approach it. Model drift is the degradation of a machine learning model's performance over time because the data patterns in production change compared to the data used during training. In simple terms, the model was trained on one type of data distribution, but real-world data evolves, causing prediction accuracy to decrease. There are mainly two common types of drift. 1. Data drift, feature drift. The input data distribution changes. Example, customer behavior changes over time. 2. Concept drift. The relationship between input data and target output changes. Example, fraud patterns changing in banking systems. Model drift is important in production because even a highly accurate model can become unreliable if not continuously monitored. In MLOps, drift detection is usually handled using monitoring tools, statistical checks, performance metrics, and automated retraining pipelines. Nice. Let's continue. Question 8. What is data drift? Here's a strong way to approach it. Data drift, also called feature drift, occurs when the distribution or pattern of input data changes over time compared to the data used during model training. Because of this change, the model may receive unfamiliar or different data in production, which can reduce prediction accuracy and overall model performance. Example, if a recommendation model was trained on customer behavior from last year, but user preferences change over time, the incoming production data may no longer match the training data distribution. Common causes of data drift include changes in user behavior, seasonal trends, market changes, new data sources, sensor or application changes. In MLOps, data drift is detected using monitoring tools, statistical tests, and data quality checks, and it often triggers model retraining or pipeline updates. Great. Moving on. That wraps up this episode. Nice work practicing, and see you in the next one.